Good morning, everybody. My name is Manos Tentzeris. I'm Ken Vice Professor in Flexible Electronics with Georgia Tech and also chairing the IEEE EPS RF and Terahertz Technology Technical Committee. I would like to welcome you to this supplementary presentation contributed by our technical committee, focusing on additively manufactured zero-power wireless modules and systems. Presentation with review recent achievements in terms of interconnects, packaging, modules, and systems over a wide range of frequencies, going from megahertz to terahertz, with applications to IoT, smart agriculture, smart skins, machine-to-machine, and smart. The technical committee contributing in this presentation is the IEEE EPS RF and terahertz technologies, focusing on components, modules, and materials for RF, terahertz, and wireless applications, including packaging structures, module systems, bound wearable applications, metamaterials, wireless sensors and nano sensors, RFID-enabled systems, MEMS, green RF electronics, wireless power transfer and energy harvesting, nanotechnology-based RF structures, high-performance passives and interconnects, and then low-power, zero-power RF modules, additive manufactured RF systems, and flexible RF. Our technical committee includes 28 members from all over the world. I chair the committee. Here is my contact information with the co-chair, Dr. Prem Chahal from Michigan State University. RFTT Technical Committee has also multiple subcommittees focusing on different topical interests, RF and terahertz packaging modules and components, co-design, optimization, and modeling of high-performance passives interconnects, 5G and 6G communication and radar systems, wearable biomedical packaging components and sensors, additive manufacturing and flexible packaging, system-level multi-physics, mixed signal co-design for high-speed and mixed signal, for example, optical systems, Internet of Things, artificial intelligence, and cyber-physical systems such as wireless sensors. RFTT is working very closely with ECTC Technical Review Committee of High-Speed Wireless and Components, HSWC, chaired by Dr. Lianjun Liu from NXP Semiconductors. Here is the information for the homepage and also the webmaster name in case you would like to contribute some research achievements or catch up with the latest activities of our technical committee. I would like to invite all of you that may be interested in any of the topics of our subcommittee to contact me, Dr. Chahal or Dr. Liu, to either join specific subcommittees or get involved in ECTC contribution. One of the main application scenario of most of our efforts is something we call Cosmos, computational skins for multifunctional objects and systems. That means arrays of dense, high-performance, seamlessly networked, ambiently powered computational nodes, communication nodes, sensing nodes that are embedded pretty much on everyday objects. Objects that consist of materials that are non-optimized for electronics, such as tissues, fabrics, floors, walls, paper for sticky notes, packaging configurations, dense high-performance RF modules that can enable smart city, enable smart manufacturing, mobility Wi-Fi, smart digital citizens, smart health, smart agriculture, smart grid, smart buildings, smart transportation, in a variety of standards and applications. That's a major challenge for the current state-of-the-art RF modules, packages, and systems, as they have to encompass different frequency ranges. They have to operate in various rugged environments, and also they have to operate with very scarce power, while they need to be highly scalable, especially for sensors or IoT systems.
The current IoT is expensive and unsustainable. In the Athena lab, we develop technologies that will enable future IoT, where, for instance, customers can print their devices at home, where sensors are embedded in our environment and do not require maintenance. An IoT that is easy and cost-effective enough for everyone to adopt. The current IoT is expensive and unsustainable. In the Athena lab, we develop technologies that will enable future IoT, where, for instance, customers can print their devices at home, where sensors are embedded in the environment and do not require maintenance. An IoT that is easy and cost-effective enough for everyone to adopt.
Here you see the evolution of materials and functionalities over the last 25 years. Starting from the conventional printed wire boards, fully planar, fully 2D, that limited the amount of complexity, limited the applicability to scenario. Then moving to mid-90s, early 2000s, low temperature co-fired ceramic, another similar technologies that enable for the first time the 3D multi-layer integration. Mid-2000s, liquid crystal polymer and other polymers that enable for the first time the first flexible RF modules. And now we're in the most challenging case, investigating modules on PET carton, paper, fabric, glass, and pretty much on every substrate. In terms of functionalities, 3D multi-layer now has become a commonplace. MEMS integration for low power switching and high efficiency passives have been integrated in an ever increasing number of RF modules. Thermal solutions that can be integrated within the module in configurations to the 3D configurations is also very common, and also nanotechnology is increasingly affecting materials, systems, sensors, and so on. If we look at some generic schematic of the RF or even mixed signal modules of the future, we'll focus on the following. Pretty much they have to perform tricorder operation. So for some fraction of the time they have to do communication, some fraction of the time sensing, some fraction of the time they have to do energy harvesting. So you need to have a multi-mode, multi-frequency wireless interface for communication, sensing, and energy harvesting. Some substrate that could encompass or encapsulate ICs performing sensing, power management, communication, silicon CMOS or other semiconductive substrates, and then electronic interfaces for nanomaterials. Nanomaterials for sensing, harvesting, energy storage, which will lead to a second multi-mode nanowire interface. And that's a major challenge, especially for applications for Internet of Things, smart agriculture, smart cities, that have a very large variety of very stringent requirements. Range, miniaturization, data rate, integrability, mass scalability, smart and possibly a self-monitoring, self-diagnostic, possibly self-healing packaging, flexibility, power autonomy, ID resolution, secure EMI immunity, and also counterfeiting. So right now we're in a very interesting situation where constellation of technologies have converged to enable these systems. First of all, 5G, 5G plus networks. They have enabled ultrafast, ultrabroadband communications in an unprecedented fashion. Not only because peak data rate now can be 10 to 20 times better, or air traffic capacity 10 times, network energy efficiency 100 times better, but also because connection density can be at least 10 times and latency 10 times better compared to the 4G systems, allowing to have for the first time truly ubiquitous applications, applications covering coverage of machine-to-machine communication, real car autonomy, level 3, possibly level 4, wearable devices that are very autonomous, very flexible, but also multi-sensing capabilities, with a very non-invasive configuration, massive antenna arrays, digital signage, and so on. In addition, additive manufacturing technologies have revolutionized manufacturing. Inkjet printing, aerosol printing, 3D printing have enabled truly 3D RF modules, such as this one shown in the middle. RF modules that can integrate IC with different thicknesses, interconnects that are not only vertical but also oblique configuration in 2D and 3D, smart encapsulations on demand, pattern ground planes, easily integrable passive components, antenna filter balloons, as well as thermal solutions that can be very easily customized to different module sizes and requirements. Here you see some examples. Inkjet printing. You see a fully inkjet printed antenna array with a patterned substrate, as well as fully printable feeding line, grounds, and so on. On-chip antenna, ramp interconnects, ramp 3D interconnects, who have proven to be a great alternative and a great substitute for wire bonds. They're more rugged, much lower parasitics, operating at very wide frequency ranges, and that can be fully additive manufacturing. 3D edge interconnects, and then whole modules. In addition, 3D printing has enabled fully 3D structures, such as this biconical selective sensing antenna, smart encapsulation over an IC with on-demand optical, transparent, or opaqueness performance, as well as fully integrated frequency selective surface to minimize interference from neighbor interferers, patent microfluidic channel, and substrate integrated waveguide at the same time. Individual element lens that can significantly enhance point-to-point, point-to-multipoint wireless communication, fully printable ramp interconnects from one level to the other, and also fully flexible, fully twistable waveguides for higher frequency applications. Backscattering also is a technology that has been exploited mainly over the last 5 years, enabling zero power operability, enabling operability communication between wireless modules and a collection gateway, software-defined radio or other type of gateway without needing batteries. Here you see an example for a wearable sensor system where the local collection point gets the energy from a handheld two-way talk radio, interrogates the wearable sensors, gets the data, and then transmits to distances more than 10 meters to get away without the need of a battery. Here's another example with some UAV monitoring for smart agriculture, taking advantage of, for example, nearby music stations and their reflected signals. It's very easy to get properties, get information, get data with gigabit per second backscattering data rates, and with a power efficiency much better than 0.15 picojoules per bit at interrogation ranges of kilometers in a fully scalable, ultra low cost. Really, really important for smart house, smart cities, smart configurations. So slowly we are moving to the Internet of Smart Skins. Instead of having the conventional bulky RF modules, we're moving to thin, flexible devices, thin, flexible configurations, as we call the skins, operating at very low powers, below 20 microwatts, that are completely batteryless. That means utilize energy just from ambient energy harvesting, with some very significant interrogation capability, like long range in excess of 250 meters. That can be localizable in real time with centimeter accuracy with just a single reader in both angle and range. These modules have to be agnostic of the mount and substrate, even for metals, and they have been significantly enhanced by 5G plus 6G. Here you see a couple of examples of Vanata modules. You can see very easily how printable the whole system is. The antenna array, the Vanata, the solar cell, everything but the ICs has been printed in some flexible configuration that can be encapsulated or on demand. Here you see also the first fully printed autonomous wireless module, 5G 28 gigahertz, and how easy the realization of this module is. That's a 28 gigahertz backscatter RFID enabled module with a package integrated energy harvested to power it up. This has been printed utilizing SLA 3D printer to fabricate the SOP package with cavity and ramped sidewalls. You see the ramp sidewalls here. That means metallized in oblique angle sides of a cavity. And also Inkjet-Printed 3D ramped vias and 26 GHz antenna array. So here are the fabrication steps. It's quite straightforward. 3D printed substrate with cavities, via holes and ramps. Inkjet-Printed SUA for planarization. Inkjet-Printed conductive traces and filling of ground and via. Flip chip IC bonding and then filling of the cavity with any filling or encapsulation material you prefer. Then printing some planarized in SU8 and on top printing the antenna on the top layer or the antennas on the top layer. So you can see here by just utilizing a conventional 3D and an inkjet printer, you can come up with quite a complicated RF module with virtually every common component: antennas, ICs, energy harvesters, ramp interconnects, printed cavity, printed ramps for interconnects, even diodes and lines. Another technology that has enabled a new, very powerful generation of RF modules is something we call the shape morphing technology. So utilizing origami or tessellation principles and then smartly or intelligently modifying the shape of the RF modules, we can have operability of very wide frequency band and over multiple standards, which has been one of the limiting factors for practical IoT or smart city implementations. You see some examples. You can have some zipper origami Voronoi scaffolding structure, and then you can print on top of these multiple antennas a helical antenna that can be filled by liquid metal, a zigzag antenna. You could have multiple antennas and multiple sensors on it, while you could also embed in these control porosity ponds multiple electronics. So slowly, utilizing this shape morphing capability and choosing the appropriate folding, you can have virtually unlimited reconfiguration states, much more than the MEMS. Now obviously this one sets new packaging, new integration challenges. Most of them can be addressed very effectively utilizing well-designed hinges. Here is a schematic of 3D printed hinges that can enable the folding in one or two directions, or that can enable the folding from a planar shape to a 3D shape like a cube here, or like a tetrahedra here. So doing that now, we can slowly start thinking about fully 3D packages or packages that change shape and features based on the environment. For example, you could expose different layers of the package, modifying the frequency bands you have to reject in case there are multiple interferers. You can change the shape of your module if you have metals around you. So here's an example. You would have two antennas, fully planar configuration. If there is no metal, if there is metal in the bottom, the sides fold in a cubic configuration, and now you have a very effective performance. And you can see here how large the dynamic range is. So slowly now, the shape becomes the reconfiguration factor. The shape becomes the factor that affects the electrical performance. The package itself can readjust to different conditions. And also, as you can see here, this is a very rugged configuration. Power is also a very significant requirement in these configurations. And ambient energy harvesting has played a significant role to come up with truly zero power. Electromagnetic waves coming out of base stations, 4G, 5G base stations, TV stations, radio stations, vibration, car, megastructures like bridges, heat, light, temperature gradients, and so on, are quite significant to power now a variety of devices ranging from sensors to more power-hungry devices like screens, cameras, and so on. So small amounts of energy converted maybe through piezoelectricity, electrodes, solar lights, radio waves, thermoelectricity can power up systems requiring milliwatts of energy. Here's an example of ambient electromagnetic energy fully printed scattered on paper substrate that can be embedded virtually every package or module 6.5 kilometers away from a TV station, harvests 100 microwatts, and then by using dynamic duty cycle, this one can power up lots of devices requiring milliwatts or tens of milliwatts. This can be utilized, that can be printed on top of an IC, for example, for different frequencies. So having some ICs operating at 10, 14, 28, 40 gigahertz, for example, for 5G, you can print a harvester on top of the IC, harvesting stray energy and then reutilizing this to realize really intelligent packages providing information about the integrity of the IC or of the package itself. You can integrate around the module. But one of the questions typically has to do with the following fact. Okay, let's say you have an electromagnetic harvester. Many times the position or the orientation of the stronger source is not well known, or you hold this module in arbitrary orientations. So agnostic ambient energy harvesting is very important. That means you need to have a harvester capable of getting energy from different directions, different sources, different frequencies, and combine very effectively. And here's an example. For multi-beam coverage, using an RF combiner, DC combiner, and also a printable 2D lens that allows just that. Allows the fact that you can harvest sources over very wide frequency ranges. So going from FM, VHF, UHF, Wi-Fi, or even higher, or even millimeter wave, you can come up with tens of milliwatts. In addition, doing that, you could combine very effectively multiple energy sources as solar, thermal, vibration, RF, store them either to a dielectric supercap, pseudocap, battery, and so on, and then activate your devices on demand. Here you see also an idea of the smart packaging we discussed before. Up to very recently, most of the people have been thinking of package or enclosure as a means to protect mechanically, maybe thermally, your module or your electronics. But now we're moving through the use of additively manufacturing to a new generation of self-monitoring, anti-counterfeiting, self-diagnostic, or possibly self-healing RF packaging structures and modules. Very easily, you can embed fingerprinting resonators or sensors within the packets that can be effectively interrogated by some gateway and then monitor the anti-counterfeit of the IC while also detecting a signature, giving an idea about the integrity of the package. This can be done in 2D, but also it can be done in 3 dimensions to make some systems much more powerful than typical anti-counterfeiting configurations by just embedding fingerprint resonators and sensors in arbitrary configurations. It's literally impossible for a counterfeiter to replicate that. In addition to this, slowly it has become possible to even embed electrochemical cells or some power sources that can effectively reset your module if somebody tries to tamper with that. Obviously, these enclosures, these packages, can take arbitrary shapes, not only rectangular ones. They could be pyramidal ones, they could be prismatic ones. And also, they can very easily integrate other systems, such as frequency selective surfaces that could very effectively minimize interference. Sensors typically have been in the past very bulky, creating lots of problems and complicated their integration with RF modules. But now, using additive manufacturing, easily you can come up with zero power wireless sensors. Here you see how easy it is to do some liquid sensing that could be utilized, for example, for microfluidic heat monitoring. So based on the solution, based on temperature, you can change the electrical properties, the electric constant, permittivity or resistivity. And also here is a fully printable gas sensor in case you want to monitor outgassing, or in case you want to monitor integrity of the package against water vapors and hydrogen. So easily utilizing pretty much ambient sources and taking advantage of the zero power sensing, you can very easily monitor the status of your module, the status of your electronics, the status of your package very effectively, just converting information to micro. That's an example about smarter strips utilizing Inkjet-Printed microfluidics. Microfluidics can be very effectively integrated to modules using printing technologies, additive manufacturing. You see here standalone microfluidics, paper microfluidics, liquid inlet, antenna, lines, pretty much everything. All these components, along with 6 sensors, can be printed. And the only non-printed part is the RFID chip, where the interconnects, the ramp interconnects, can be printed very effectively. This one is very tiny, that's realized on paper substrate, very miniaturized, very scalable, and you could have on-demand sensors. Sensors that can find application for a variety of applications. Biomonitoring, health monitoring, even COVID detection, antibody detection, to chemical sensing in industry, sensing for cars, temperature sensing as well. Here is another printable smart agricultural sensor. You see there's a leaf wetness sensor, interdigitated, that performs rainfall and frost detection, soil moisture sensor, and then a dual band antenna, an antenna which has a long S shape, which performs energy harvesting from local VHF, UHF TV stations, and the short strip printed that can transmit the sensing data to some gateway at a large distance. So the microcontroller is not printable. Everything else has been done quite on paper. The whole idea is that utilizing just 2 antennas and a gap with functionalized printed graphene or functionalized printed carbon nanotubes, which can be done very routinely, leads to a frequency shift and also reflected power shift that can give a very clear idea using 2 degrees of freedom of the detected not only presence but also identity. Another example shown here, electronic nose, any substrate, any functionalized sensing material, and then electrodes on top of this. You can have multiple sensors coexisting, and in this case you could have sensitivity chipless sensing, 50 ppb at 50 meter plus range in seconds. That would be tremendous if you can integrate this in multiple packages by just printing some multi-finger configurations operating at frequencies. That's another example for structural health monitoring, strain sensing modules requiring flexible packaging. That's another major requirement, flexible rugged packaging that does not affect the stressing or the strain detection. I will close with this slide, smart floating balls, because I want to stress the future of the RF modules. Up to now have been used to 2.5D modules. Modules that have parallel layers where we integrate ICs, where we integrate interconnects and so on. But slowly with additive manufacturing, we're moving to truly 3D modules. Modules such as this one, where you have, let's say, 4 conformal antennas, you have a conformal ground plane, you have phase delay lines, packaged and enclosed inside, liquid channel, all of them performing water quality monitoring. And this one is spherical. There is a multiple number, an ever-increasing number of different shapes, requiring now smart on-demand arbitrary shape packages, which is going to be a major, one of the major challenges of the future. With this, I would like to close. Thanks for watching this presentation. Technologies such as 5G, additive manufacturing, backscattering, and origami shape morphing have revolutionized the shape and the performance and the ultra-broadband, ultra-fast capabilities of RF modules. Lots of challenges have been addressed. Right now, we have more and more modules operating in millimeter wave or even sub-terahertz. It's possible to have on-demand modules, on-demand shape, on-demand packages with very scarce power, but there are lots of challenges to be addressed. So we're looking forward to the papers of the future. Look forward to meet you all personally in ECTC 2021. Stay safe and healthy, and feel free to contact us if you would like to join our RFTT committee. Thank you very much and enjoy the virtual conference. Thanks.